This is Unsmashing the Stack, Overflow's Countermeasures in the Real World. My name is Sean Moyer. I work for a security consulting company in St. Louis called Speartip Technologies. These talks tend to be, this is my third one, and they tend to just be on something that I'm interested in and kind of obsessing about. So this is sort of what I've been obsessing about for the past year or so. We do forensics, we do assessments, we do a lot of IRDF, and so part of where this comes about is kind of my interest in going through and dealing with compromises and break-ins and thinking about some of the stack protection mechanisms. I mean, most of the time, whenever I'm dealing with a compromise, it usually starts with a buffer overflow of some kind in a network service. So, sort of the question of what can we do about that stuff. I like unsolvable problems, so I think probably more about defense. I think that the whole separation of attacker-defender is kind of pedestrian. I don't think it really is quite that simple. And actually, what I'll say is if you tend to be more interested in the attack side, a lot of what I went through in this talk in trying to kind of figure out how some of the protection mechanisms work, I also found a lot of things about attack vectors that people hadn't thought about. And that's, I think that's really the point, is a lot of these things do overlap. And there's sort of the two that kind of flow with each other. So I'm just a regular guy. There's a lot of really smart people at Black Hat. I'm not one of those people. This is, in particular, what I would say is I'm not an exploit developer. I've surprised myself in talking to people this year about this topic that I'm kind of able to hold my own, but, like probably the majority of people in this track, most of what I work on a day-to-day basis is the defensive side, and I've been in InfoSec for about 12 years and always been on the defensive side, so I found myself not really having to think a whole lot about the internals of a given vulnerability or how these things kind of work. Most of the time in the defense side, it's just, oh crap, we got a patch, we're all kind of scrambling to do that. And so with Vista and with some of the other things we're going to talk about overflow protection mechanisms that are kind of starting to come about in a lot of the different platforms, I wanted to kind of understand the effectiveness of sort of how they work. So pretty much I had an interest in this topic. One of the things that I found when I looked at this is that every paper I found and every talk that I found was either written by somebody who had came up with a way to defeat a given protection mechanism or somebody who was the author of a given protection mechanism. And of course, the people defeating it said that this was an ironclad attack, and of course the people writing the protection mechanisms always said that it was an unbreakable defense. So I'm kind of trying to see if there's some middle ground in there. Something that I mentioned in the paper is that the security industry as a whole, we've been on this cycle now for 10, 12 years where we've sort of applied the same model that the antivirus industry sort of perfected in the 80s, where it's about patches for sale on a subscription basis and going through and releasing signatures and patches and updates. And now, you've got the hot patch vendors doing some of the same things. But the question is, ultimately, what's kind of the root of the problem, and where does it, is there anything that we can do to address it more at the core and maybe get out of this sort of flailing death loop that we're in? So, what is this stuff? It seems like, in particular, kind of in the past few days when people ask me, like, what am I talking about, I've found myself saying exploit mitigation. At first I said pro-police ASLR, no exec stacks, and, people just looked at me. So, I think exploit mitigation is probably a pretty good term for kind of what this sort of series of different technologies do. The main intent of all this stuff is to make mass exploitation tougher to do. It's not necessarily about making something completely unbreakable, but at least, Mike Howard from Microsoft, who's one of the architects of some of this stuff in Vista, he calls it creating diversity. That you're trying to make things not so heterogeneous, homogeneous, where things are all kind of the same. I think a lot of people don't realize that most exploits are about kind of known configurations and known systems and being able to predict some of that stuff. And we'll get into more of that when we start talking about ASLR. Like I say, we're going to go over non-executable stacks and some of that stuff. address space layout randomization, canary values, some things about better organization for memory space, some of the things that you can do in compiler, and also look at some kind of other ways to approach this in terms of containment and things for exploits. So kind of starting at the beginning, does anybody know who these guys are? Somebody, come on. Allen and Gates. Yeah, so yeah, this is yeah, somebody said K&R. It's actually, I was looking for a picture of K&R, and I couldn't find one of both of them together, so this is Thompson and Ritchie. And I think Ritchie is the guy with the Phil Collins haircut. You know, he's always had like the kind of the bald on top and the long and back thing going on. But, you know, when we talk about this at a fundamental level, you know, when these guys came up with the C programming language and when we were initially kind of defining the architectures and the models that we use for computing, those are the 2 points into that system. That teletype, the other teletype. So when you're dealing with a bad actor or somebody who's, you know, a threat or an adversary, you can elbow the guy and say, hey, cut it out, Bob. You know, so it's a whole different problem than what we're dealing with now 30-odd years later. And actually, I was talking to somebody the other day about, has anybody ever messed with Core Wars years and years ago? If you like old stuff, you're a retro kind of guy. Core Wars was a game on some of the early Unix systems where you actually sat there with an adversary and played with like writing ASM instructions and then trying to stop the other guys. You know, and we're still playing Core Wars. It's just a little bit more complicated now. You know. So, you know, this class of bugs has probably been around longer than, you know, just about everybody in this room. Was anybody born before 1948? You don't have to raise your hand. You know, a lot of people will say it goes back to the 60s. I would actually, as I started trying to kind of understand the problem, something that I found actually in some previous documentation is they talked about the von Neumann model. And von Neumann was actually one of the guys from the Manhattan Project. Who was involved with UNIVAC and ENIAC and some of the early computer systems. And, you know, in the very first systems, the way that you reprogrammed was to resolder. You know, you take apart a system and rewire it. And so von Neumann came up with a data code abstraction. So it was the idea of you have a series of instructions, and then you have data that you feed to, you know, an operating system, and then you deal with those instructions. Well, pretty much everything in dealing with overflows and memory corruption-based attacks is about jumping across that membrane and inserting data, unexpected data, that jumps across to the code layer. So what we're dealing with now with exploit mitigation in the last kind of 5-6 years is like trying to shore up that membrane and trying to kind of lock it down. So, you know, some of the old terms, you know, Fandango on core I really like. You know, I wish that would have stuck instead of buffer overflows. You know, I would have liked to have seen, you know, MSO4-27 Fandango on core and IIS, you know. But, you know, for whatever reason that didn't stick. I had to actually look up what a Fandango was, and I guess it's a Brazilian dance where there's like kind of a two-step that you do, so you're jumping from data to code. You know, something else I found was in Algol and Fortran and some of the early high-level languages. You know, they talked about dangling pointers and stale pointers, and of course, if anybody saw the talk yesterday, we're kind of now like just starting to wrap around that one. So, going back and trying to kind of understand, you know, where did this stuff start? Kind of the first remotely exploited buffer overflow was one of the two vectors that the Morris worm took advantage of. So there was a stack-based overflow in FingerD, and the Morris worm code, actually, if you look at it, it's 99 lines of C, and it's you know, it has all the same principles that stuff still has now. You know, shell code and overriding pointers and redirecting execution flow. So it's kind of all the same principles. It's actually bug ID number 2 on Security Focus, which I thought was pretty cool. Somebody, whenever they were creating that database, kind of stepped back and said, okay, that's number 2. Number 1 is sendmail debug, you know, and that makes sense to me. So we're still kind of dealing with that one. FingerD is not in as wide use now, so we haven't sort of seen the same problems with it. The other thing that really was compelling to me is Spaff, Gene Spafford, who was kind of one of the first people to sort of define the InfoSec field and how this stuff works. He talked about bounds checking in C and said, you know, we need to avoid the gets call, the scanf call. We need to replace those with you know, sanity checking alternatives. And there's a whole section he's got in, basically that was kind of what he felt was the key problem with the Morris worm. So, the answer is we've known about this stuff. It's been quantified and defined for at least 19 years. So, things were kind of quiet on the overflow front from about 88 to 95. If you look at the old bug track stuff back then, it was really just kind of, stupid developer tricks, like things like, really poor handling of login and authentication. I mean, I know if you look into like some of the old VAX bugs in the 80s, they were things like, hitting enter twice on login would drop you to an admin prompt, But once we started to fine-tune things a little bit and kind of shore up some of the really obvious stuff, we started looking at overflows. And Thomas Lopatic, who, if you look at some of the other things he did, he found some of the IIS bugs that related to NIMDA and some of the more widely exploitable 1990s stuff in IIS. He found a stack-based overflow in the NCSA HDBD. And if you read his post, he says, hey, this looks just like the Morris worm. And what was interesting about that and why that became sort of getting everybody interested in this problem is that this was as the public internet was starting to come about and we were starting to be interconnected. So these were no longer things that you could exploit on a local LAN. They were things that you could do from anywhere over the internet. And that's kind of really when things took off. Mudge wrote a paper that was a kind of a precursor to Aleph-1. We'll get to Aleph-1 in a second. That was an early walkthrough. He talked about constructing shellcode, NOP sleds, a lot of the same things that are still being utilized. Aleph-1, obviously, I'm assuming most of you have probably read Smashing the Stack for Fun and Profit. It still gets referenced. Like, one of the things that I found when I was trying to sort of understand this problem is that I couldn't find a single book that talked about exploitation that didn't reference that somewhere. And actually, something that I was impressed by now is that I found, just sort of like if you just Google for a copy of it, that there's a lot of university websites and a lot of professors are actually having their kids, their students walk through and write vulnerable code and understand how it's exploited. So, if the previous generation of developers had kind of had some of that exposure, maybe we wouldn't be sort of in the spot we're in today. Solar Designer in '97 was the first, and seems to be agreed upon to be the first example of return to libc-based attacks. This was actually, he was the author of one of the first no-exec stack implementations, and he, in discussing integrating that patch into the Linux kernel back then, actually, if you look through some of the threads, Linus Torvalds and some of the other guys said, hey, wait a minute, this doesn't really help you that much. There's still other vectors, and that he kind of got to thinking about how return to libc stuff works. So instead of exploiting something on the stack, you're targeting preloaded functions, things in memory. After that, probably the next leap in exploit development stuff and sort of attack approaches was the Woo-Woo paper on exploiting heap overflows. It was really interesting to me as I was trying to understand heap overflows that there's like a lot of discussion about it now. There's a talk at DC about it. And thanks for coming here instead, but there's the Soderov talk on the heap, feng shui, and JavaScript stuff. So it's still kind of an area of a lot of interest. So I had fun with it. I'm kind of a retro guy. I like kind of understanding some of this. For me, I was around and was kind of in the industry, but I was just getting my brain. I was a little kind of, somebody said, a little hackling, and I was just kind of starting to understand this when all these things were going on. So I liked, it made me feel better to kind of run back through some of this and realize, okay, yeah, I guess I've learned something because I understand a little more of this now than I did. The reason that we care is that fundamentally hitting the stack, return to libc, and hitting the heap, in addition to format strings and, of course, the whole user-based, and user-based exploit stuff, which is a whole different can of worms. But as far as targeting kind of memory corruption vulnerabilities, that's still kind of, those are still the main approaches. It's just we've sort of fine-tuned how we do it. This is National Vulnerability Database, remote buffer overflows up to 06. I know that there's some questions about how these stats are gathered and everything else, but I think that the main thing that we can agree on is that the problem hasn't got a whole lot better. And we've continued to see remote overflows as one of the more common methods of remote exploitation. So at a very high level, and I know there's going to be errors in this, and you could probably pick it apart, but at a very high level, you're taking a unchecked allocation of memory somewhere, you're inserting input, and you're targeting either the stack or the heap, preloaded functions in memory. You're moving execution flow to take advantage of what you've inserted into memory, and then that allows you to control execution flow. So that's fundamentally the problem. So the first kind of approach to this, and going back to some of the von Neumann model and the data code separation stuff, the first kind of approach to this was the no exec stack. And fundamentally what that does, we'll get into some of the specifics of how some of the approaches work, but at a very high level, what you're doing is you're creating a data code abstraction, say kind of going back to von Neumann, and you have instructions and you have input and data, you're separating those out and you're creating a wall between them. Essentially the problem here is that if you have unchecked input, that then allows you to insert instructions, and then you jump to those instructions. That's what a stack-based overflow does. So actually a little bit before some of the emulation stuff, you had the no exec stack bit in Solaris. If anybody worked a lot with Solaris, I did a lot with Solaris in the 90s. We used to always congratulate ourselves on that. Yeah, we've got a no exec stack. All the hardening scripts and things like that would always set that bit. And it's like, hey, we're safe. We're great. So HBUX and some of the other Unixes also had similar implementations. Nowadays, we have the NX bit, which is kind of rewinding back to that same principle. Part of this is related to the fact that on 64-bit architectures, you have better memory management than you do on a 32-bit arch. So you have the page address extension, gives you an ability to separate memory pages in a more granular kind of way than you do on 32-bit, where it's more kind of a blob. Something to point out is that all the different implementations of NX or XD or anything else, whatever you want to call it, require you in the operating system to take advantage of that bit. It's not something that just sort of runs by itself. And we'll get to that in a minute in terms of how that's applicable to some of the methods to circumvent it. The emulation software stuff is an approach to kind of get the same thing on an IA32 platform that's not as granular as 64. You have the WXORX stuff in OpenBSD. ExecShield is a Red Hat technology, and then there's PAX and DEP, which is the Windows one that probably most folks are familiar with. They are less fine-grained. There have been some things that talk about taking advantage of the fact that it's not quite as granular. If you run into, as I understand it, if you run into something where you have memory allocations that are a little bit smaller than what you can kind of break down easily into two segments, sometimes the software implementations will exempt themselves and say, okay, I'm not going to actually take advantage of the separation. And there have been some exploits that take advantage of that. But on 32-bit, it's something, and it's more than what you have without it. One of the things that you run into with no exec stacks is that it's problematic for applications that want to construct code on the stack. JIT compilers, Java, .NET's, Java runtime, anything that does emulation and things like that, they're going to expect to have that functionality. And where that gets interesting is that what that has meant is that in a lot of the platforms, they've had to build ways to opt out and exempt yourself from that. And so some of the attacks have taken advantage of that. And so sort of on to the attacks against no exec, the vulnerability is still there. You've basically reduced it down. You've removed sort of one vector and one method of exploitation, but you haven't removed the vulnerability. And you've simply just made it a little more difficult to exploit. So return to libc, we talked about that earlier with Solar Designer. Most of the talks I found on OwnDep or OwnNX, they all talked about a lot of different stuff and made it sound a lot more complicated than it really is. But fundamentally, what most of those are about is return to libc. Just calling an existing preloaded function something in memory as opposed to actually inserting shellcode. One of the other things which I was actually talking to somebody about earlier, Dave Litchfield has done some work with doing return to libc, calling mprotect, and mprotect is a function that allows you to say, kind of leave my stuff alone and exempt yourself out of the model. So it's possible to do return to libc and then jump to mprotect and insert things onto the stack, and then they're left alone. It requires, with return to libc, a known address, a useful function in memory. We always kind of refer to it as return to libc. It's typically return to system, return to winexec. So we're just calling functions that run code that are in the kind of the standard runtime libraries for a given OS. Heap-based overflows, no exec stack doesn't apply. Fundamentally, what you're doing with a no exec stack is you're just saying this specific set of conditions, which is I'm inserting data and I'm jumping to it, or inserting code into a data segment and jumping to it. So it doesn't do you any good on the heap. It doesn't do you any good with return to libc. Justin of Bioactive did a talk yesterday on DL Malloc. There is an Atlas talk if you're going to DEF CON that's also on heap exploitation that is probably of interest. And there's the Ollie Whitehouse talk, which talks about some of the specific ways that Vista does heap allocation stuff. One of the other ones that I found was an academic paper by Piramposa and Embody, and I guess Embody did a talk here. I think they're from UMich, if I'm not mistaken. But the Hannibal attack concept that they came out with was to insert a pointer in a vulnerable segment for some arbitrary address somewhere, and then as the second step, insert your payload, and then get execution to jump to that payload. The thing about that is, what it doesn't do that a traditional stack-based overflow does is take data and jump over to code. So again, the NX just becomes, Dave Maynard called it a couple of years ago in his talk on DEP and NX a speed bump. It's just enough to make it just a little bit trickier. But actually, if you look at exploits today, as more and more platforms have no exec stacks, and in fact, I would say that pretty much everybody at this point in the past 2 years has some kind of stack execution, implementation that prevents that. It's been not a barrier at all. People have sort of engineered around it and sort of expected it. If you look around Millworm, there is a guy in South Korea, who has a whole bunch of papers about dealing with Red Hat's exec shield, and he's sort of perfected it. So Red Hat is, a pretty solid no exec implementation on Red Hat Enterprise 4, and so just about every kind of stack-based vulnerability, he's just jumped right through their exec shield implementation. This one was kind of interesting to me. Escape and Skywing did a paper on MS's step. Something that MS does with their no exec implementation that's a little bit different is that it's a runtime flag. So it's in memory, and for a running process, you're setting some bits to define whether you're executable or not. So what they found was that you could flip those flags, and then again, this was sort of via return to libc. You could then flip those flags for something that's vulnerable and then take advantage of stack-based overflow. So it became just totally irrelevant. The point of that, if you have, and this isn't something you can necessarily do on a desktop, but if you have Windows-based servers, go into your boot INI. It's documented by MS, but it's not something you can do in the GUI. Go into your boot INI and set no execute equals always on, and that means there's no opt-out to it. Basically, the other two options, which are all Windows services or on by default but allow apps to opt out, that process execute flag is what you're setting when you say opt out. So if that can be controlled on the fly, it's really irrelevant. PAX is another no exec implementation. They do this in a file header, so they have some bits in the ELF header that give you a way to set that. Potentially, I think that might be a higher bar and kind of a better middle ground to allow you to exempt things that don't get along with no exec stacks, but still have a little better protection. Some more opt-in, kind of opt-out ugliness. Everybody's implementation allows you to disable checks at runtime or in compile time. Virtual Protect and mprotect both give you the ability to set particular areas of memory as being exempted from the model. Skywing has, related to that same paper, he has a no exec Hall of Shame. I've kind of found this too in running with no exec stack without the, in Windows without the option to opt out of it, that lots of things that you wouldn't expect to crash will just blow up. So personally for me, Firefox, Acrobat just die just all the time. And I'm sure that it's because they're making an mprotect call somewhere and then it's falling over. Something that I actually stumbled across as far as no exec stacks was a number of years ago I was running an app called Secure Stack, which is a add-on for Windows. Actually at the time it was NT4 that does a software-based no exec stack on Windows. And I had a backup guy, admin guy that pushed backups, backup administrator, and he was trying to do a code update to backup exec, and it crashed all the boxes running the agents because he had the secure stack stuff. And what was interesting about that was about maybe 2 years later, there was a stack-based overflow in backup exec. So, I kind of wonder if the things that break maybe be breaking, they may be breaking for a reason. So kind of the next step was to go to canary-based stuff and look at checking for corruption of memory in the stack itself. StackGuard was the first approach, and this was Crispin Cowan, who's also the author of AppArmor. What you're doing is putting a canary value somewhere in the stack for the return address, and when the canary value changes, that means the return address has been overwritten. Later versions, he added some more features, and actually there's StackGuard, PointGuard, I think there's HeapGuard, FormatGuard, I know there is. So they kind of started adding a lot of other stuff, but the main problem with the Munich stuff was it was very x86 centric, so it didn't really get picked up by a lot of other things, and it didn't get integrated as a whole into GCC. Which brings us to ProPolice. Very awesome stuff. Hiroki Ito of IBM was the author. The OpenBSD guys did a lot of work with it in later years. It was integrated into GCC 4.1. So this is now available in GCC for most of the major Linux Unix distros that have moved to that. So like Red Hat 5, the latest Ubuntu, and things like that are using GCC 4.1, and they do have a ProPolice implementation. MS initially was sort of based on some of the MS Canary implementations were originally based on StackGuard, and then kind of moved to stuff that's more comparable to what ProPolice does. The GS cookie is basically the ProPolice guard value. I guess I should say that Hiroki doesn't like to call it a canary, so he calls it a guard value. It is an XOR of the pointer and the random value of the pointer stored off stack. One of the big things about ProPolice is that it moves to all addresses or to all registers. In Prolog, it's a well-ordered stack. The variables and arrays are at the bottom. Actually, here's a slide about just that. For me, ProPolice, I never understood the name. What made it, a police officer. And actually, it's kind of a pun that I guess is funny to Hiroki. ProPolice is the stuff that bees use to construct their hives. And to me, that really kind of helped me understand it a little better, that it's not just a canary implementation. So what you're doing with ProPolice is you're trying to create a well-ordered stack. And so in the case of what a ProPolice safe stack looks like, you have arguments and return addresses, and then your previous frame pointer, the guard value, and then arrays and local variables separated. Most stack-based overflows are about passing things to arrays and then overriding the return address. So if you lay out your stack a little bit better, those vulnerable sections of memory are not adjacent to each other. So The well-ordered stack may be more important, actually, as far as how ProPolice works. It may actually be more important than the canary stuff. Something else that I asked a lot of people about was heap canary stuff. There's a lot of talks on the heap lately that this has become an area of a lot of interest because a lot of the exploit mitigation stuff doesn't really do much for the heap. There are a couple of implementations out there for guard pages and canary type implementations on the heap. ContraPolice is one of those. WKR, and I didn't get a chance to find out what his initials stood for. I've read some of his stuff before. He's been involved in DEF CON CTF over the years and some other things, but he did a guard page implementation for DL Malloc. The OpenBSD guys have a G option in Malloc Conf. In the case of OpenBSD, it's optional. It's not turned on by default, and the reason for that is that it does break some stuff, but it's worth looking at, especially for critical systems and things you want to protect. It is likely to be something you're going to see down the road. As the heap becomes of more interest, I think that you'll probably see this integrated more, and people are going to start to look at the same kind of method, the same kind of model of canaries and guard pages for the heap. If the canary is the key element in protecting the stack, though, the defense is only as good as the canary. So Gerardo Richart of CoreSec looked at global offset table writes and some things to the stack frame pointer. All of his stuff was specific to Stack Shield and GS and StackGuard. One of the things that the core guys say when they talk about this is they didn't find much to effectively defeat ProPolice. And I looked for information about things that were successful against ProPolice and didn't find a whole lot out there. Bulba and Killer in FRAC 56 found some other weaknesses in StackGuard, and again, I think probably the fatal flaw of StackGuard was that it primarily was just focused on return address. So because of that, any other area of memory that you could arbitrarily write to would give you the same result. And really where that came from is at the time, that was kind of the classic stack-based overflow. And so the defensive mechanism was kind of thinking about the attacks, but not thinking about all the possible vectors. One of the things about canaries is that if it is somewhere in readable memory, so format string bugs and things that lead to memory leakage may give you ways to overwrite canaries. And so there's some possible ways to get around it there. So the next step was ASLR, which is big news these days because it's in Vista. It's fundamentally misdirection. Let's shuffle address space. You have a randomized userland, kernel stack, mmap in PAX, which was kind of one of the first folks to implement this. OpenBSD has added a lot of these things. ExecShield in Red Hat does their own ASLR implementation. I have no idea why they didn't use PAX. If somebody works for Red Hat and can tell me, I'd be interested to know. But they went ahead and built their own ASLR. It's not quite as robust as PAX, but it's authored by Red Hat, so maybe that's why they like it. With Vista, we've added, random exe, DLL loaders. As Whitehouse pointed out, there's varying degrees of entropy. It's a little more predictable than it probably should be. For apps to utilize ASLR internally in Vista, you do have to pass compiler flags to do that. Like I say, it is a little bit weaker on the heap. Something with that in terms of the dynamic base stuff is PIC or PI, position-independent executables in code. Just randomizing your DLLs and just randomizing your libraries in and of itself doesn't get you a lot if the app that's running in memory still has known offsets and it's still predictable. So you really have to build executables to take advantage of that same functionality. I talked to an MS guy the other day about this, and one of the things he said is building with dynamic base in Visual Studio 05 SP1 makes apps impossible to debug, and so they really hate it because when you randomize the app, when you send somebody a crash dump, it's not applicable to them. So the developers are sort of up in arms about some of it. John Moser of Ubuntu Harden, makes an estimate that with PIC and PI, you've got stack random bits, mmap random bits, and so you increase substantially the ability to predict addresses for attacks. And like I said, it's kind of key to a full implementation of ASLR. If the app itself uses predictable addresses, ASLR really doesn't do you a whole lot of good. So what you end up with then with ASLR is brute force approaches to try to defeat the randomization. Hovav Shacham, this stuff, I didn't find a lot of people that were exposed to this guy. He is a Israeli cryptographer, and he got interested in ASLR with PAX, and he looked at this and said, hey, this is just bad crypto, right? So he built there's a paper that he's got where he built a vulnerable version of Apache, created some vulnerabilities in it, and then used a de-randomization attack to brute force the location of known offset libraries in libc and things like that, and then return to libc. So what he found was that an ASLR-protected Apache could be brute forced in about 200 seconds. So it didn't do a whole lot of good. Now that's on, and he makes a point to sort of clarify that is on a 32-bit platform, and ASLR on 64-bit is better. He has some insane new stuff about return to libc with no function calls, where he chains different sequences together. I guess I would just say, just a takeaway, something to look at. Really just mind-blowing guy. Something I'm curious about myself is Shacham on the heap. Vista does have a functionality that on restart of a service, if the service crashes and restarts like 3 times, it stops, which should help to defeat some of this. But when you're talking about things like client-side, you can try as many times as you want. And so when you're looking at the heap with weak randomization, how many tries would that take to do return to libc as like a local client-side exploit? Ben Hawks did a talk at RuxCon just a little while ago, code access brute forcing, which was a series of failed reads to infer addresses in memory. And most of what I would say about this is, and just in general, is that most of the methods to defeat ASLR relate to known offset libraries, and so you can kind of identify this looks like the system call. And so then what you're doing is just probing around in memory till you stumble across it. And then pre-linking and some of the things that you do at compile time can also make those addresses more predictable. Mentioned Ollie Whitehouse's stuff a couple of times. Very good talk if you didn't check it out. Pull the slides. So, Cliff Notes, no exec in NX. If it's runtime configurable and it's an opt-in model, it's useless. There's lots and lots of other exploitation methods. NX in and of itself doesn't do you a whole lot of good. ASLR, bad crypto, is not a panacea. Any way that you can leak addresses and any kind of vulnerability that would lead to a memory leak could give you ways to identify things in memory. So, in particular, one of the things that actually there was Tyler Durden did a FRAC paper a while back about taking format string bugs that were not exploitable but leaked memory to then find addresses to exploit with return to libc for another vulnerability. So you have like an aggregate. If your address-based randomization is identifiable in some way, then it doesn't do you a whole lot of good. Again, with canaries, it's, if it's bad crypto, it's guessable, or there's some way to get a hold of it, it doesn't do you a lot of good. Any write to memory space requires some protection. So if you're just protecting the return address, it doesn't do you a lot of good either. So the best practice, and this is kind of where we're at, this is where we sit now, is that we have the mesh model or security in depth or the onion, whatever you guys call it, of integrating a lot of ineffective measures and hope that the aggregate of all of those ineffective measures is something that's pretty effective. And from what I've read of people's analysis of Vista, and obviously people have had a lot of good things to say about OpenBSD for a number of years with some of these things. The combination of a non-executable stack, ASLR, canary values, and all of these other methods together probably does put you in a pretty good spot. So we're just getting started. It's been 19 years that we've known about sort of this problem. What else can we do to make this a little more difficult? Well, the Weld-Pond talk right after this, static code analysis. Look for things in code that are likely vectors, sources of problems. GCC Fortify Source is a series of patches that were added to GCC that do, basically they take SPAF's advice and they take things like string copy, replace it with string copy. They actually include some checks for format strings, which this is actually about the only thing I found that really does anything about format string-based stuff on an automated basis. So they will look for things that are kind of misallocated and say, you instantiated kind of this many values, and then up here you called it has fewer values than that. The Coverity DHS project was kind of big news this year. Vendor Coverity got a big contract from the DHS to do analysis of open source projects and look for vulnerabilities. We are seeing some value from what they're doing. Ben Laurie pointed out that it's really nice of DHS to fund people to look for bugs in open source code. It would be even nicer if they paid people to fix them, which is kind of part of the problem. We're identifying all this stuff, but then these projects are then now scrambling to correct the things that are found. Lots of commercial tools. Something about static code analysis. Rice's theorem. Rice, I guess, was a contemporary of Turing, and he talked about how for a given problem set, if there's a sort of an infinite number of answers, you can't really find it. And then I sort of call that Rumsfeld's corollary to Rice's theorem. We know what we know what we don't know, but we don't know what we don't know. And so, with the automated tools, there's going to be things that this will help with, but there's always going to be things that we're not going to find that way. So one of the other pieces that will help with containment of vulnerabilities is access control models. It's not specifically a method to stop an exploit, but it does help contain the exposure after the fact. You're restricting file access, you're doing things like that. The Linux world, you've got RSPAC and GRSec and AppArmor and SELinux. Does anybody use SELinux? Okay. What about GRSec or RSPAC or any of those? Cool. I've been looking more at these lately. I do a little bit with SELinux, and GRSec has been of interest because it has a lot of integration with PACS. The biggest problem with these in general is the complexity level. You have to spend a lot of time tuning, but it is another way to guarantee that exploitation is not possible if a given app can only do sort of certain things that it needs to do without breaking out of the execution space that it needs to run in. The problem sometimes with some of these is what if the exploit is still an expected behavior? So things like for a web app, if you've got a SQL injection problem, well, your app is talking to your DB. Well, it was already doing that before. It's just doing it in a different way than you expected. MS has added the mandatory integrity control stuff, the thing that we all click allow on. As pointed out next door, IE protected mode is a way to sidestep this. They run IE at a lower integrity level. Mike Howard is very hot about this, and I think that they're going to correct it over time. But IE is a big problem for this in terms of all the things that it expects to be able to do that kind of break that model. So they have it in a low security mode. On Big Iron, you've got trusted Solaris and HPUX trusted mode. Same thing. These are going to give you ways to kind of contain what apps can do. Trusted BSD is probably the only, as far as I know, the only Mac implementation. I don't think the OpenBSD guys actually have a Mac implementation as of now. If somebody wants to tell me I'm wrong, that's cool. Mac has no Mac. WWDC, there was an announcement that they were going to integrate an access control model into OS X. With the Leopard release, there's no references to it. So does anybody know if it's in there? Is it in there? Okay, I will change that before it goes out publicly. So there's no docs on your site, dude. So can I get a card from you and send me a doc? So cool, awesome. And SE Darwin was an inspiration for some of these things, which is an open source implementation based on a combination of sort of SELinux and trusted BSD. And so those were kind of integrated into Darwin. So cool. Into Leopard. So just sort of what the different implementations are and what they do. On the OpenBSD side, they've done a lot with ProPolice. You have WXRX. mProtect, there was some debate between the PAX guys and the OpenBSD guys about whether disabling the mProtect call broke POSIX. And there's a lot of contention between those two camps. They're trying to do a lot of the same things, and there's some questions about which method is better than the other. What I would like is an option to set that bit, on a given executable. I don't want to let this app mProtect, and have some kind of configurable way to do it. As far as I know, they don't have kernel K-stack randomization in the kernel stuff. So they've done a lot of things in libraries and executable space, but not down into the kernel. And so the OpenBSD kernel has been an area of interest of late. So I think that they're going to kind of extend some of that and add some more bits there. FreeBSD has just an NX bit, and that's pretty much it. If you go to that URL, and this will be out on the Black Hat site shortly, if you go to that URL, there's a series of extensions for FreeBSD for NoExec. NetBSD has added a lot of stuff with 4.0. There's that link there is a Security Focus article about some of the stuff that they've added. So they've kind of improved a lot. It's hard to talk about Linux, right? Because there's so much out there. Ubuntu and Gentoo Harden are probably the two Linux projects that have kind of got the most aggressive about adding some of these things. John Richard Moser, who kind of runs the Ubuntu Harden stuff, has a lot of really neat things to say about some of these technologies. And actually, a lot of my interest in this was from reading some of his proposals out on the Ubuntu site about how they're going to start integrating some of this stuff. So he really talks about weighing the benefit of all of the exploit mitigation stuff and how much good it really does. There's a lot of consistency issues. I mean, with GCC1 or GCC 4.1, we have the ProPolice integration, but then at compile time, if somebody has a problem with it, what are they going to do? They're going to turn it off. So there's a lot of bug reports about, hey, F-Stack Protector broke my app, so I turned it off for this RPM. So we'll kind of see what happens with some of those. So Vista, it is a lot of progress, and we're not supposed to bash MS anymore. They paid us all off. I have the invite to the super top secret Microsoft invite only party tonight, and I'm going to DEF CON instead. Sorry, but consistency is probably the biggest problem they have. They seem to be doing a really nice job of building exploit mitigation technologies into their own code, their own services, their own OS, because frankly, it's a PR problem until they solve it. But I think where the exploit space and the sort of the attack surface is going to be is things like Oracle, Symantec, third-party things that are sitting on top of it, which a lot of their technologies don't do a lot for. And the default with that in XPSP2 is protect all system services, all Microsoft stuff. So I don't blame them, and it is a hard problem to solve. It really is. They have a very diverse user base. They have a very diverse customer base, and that's a lot harder to solve than, say, OpenBSD, where they can say, okay, sorry, it's just going to be broke till we fix it. The WenTrust or WayneTrust, and I don't know how to pronounce it, the WayneUs guys have an ASLR implementation for Win2K03. So if you're running Win2K03 and you want to take advantage of some of this stuff, look at their stuff. It's very nice. And it won't give you necessarily PIC or PI in executables themselves, but you will get randomized DLLs and some of the ASLR stuff that's in Vista now. So something to check out if you're holding off on the Vista stuff till you add another 4 megs or 4 gigs of RAM to all your servers. So OS 10. Sorry, OS 10 SE Darwin guy. Right now, we've got NX in the kernel, and that has been pretty much it, at least that I could find. So in the Mac and Leopard, the question was answered. So there is an access control model for Leopard, so cool. And that is another way to approach this. But they are sitting right now probably further behind on these technologies than any other major platform. So I think in general, Apple has a lot of work to do in the security space in terms of partnering with the vulnerability research community better, understanding the problems a little better. But Mac guy at Black Hat, thank you. So good for you. So we're progressing a little bit, but I really think of Apple right now as sitting where MS did in the late 90s, of denying vulnerabilities and threatening lawsuits and sort of looking at this problem a little differently. So hopefully there'll be some progress there. We'll see. So just kind of in summary here, all these defensive measures can be defeated in a vacuum. Like I said, one of the things that I found was that a lot of the talks on this talked about some specific protection, and then here's how we broke that protection. Did anybody go to the Dave Maynard, not to pick on Dave, he gets picked on enough already, but to the Dave Maynard NX talk a couple years ago? So he did an exploit against ExecShield and how to defeat ExecShield, but he turned off ASLR. And he said, hey, don't worry about ASLR, it's not relevant to the talk. So, I think what you'll find is that vulnprog.c will always get owned. We will always have proof of concepts that defeat some of these things, but hopefully the sum of the whole is greater than its parts, and the integration of all these technologies will make this stuff a little harder to do. Something to check out, go Google for VistaProbe, and it does run on XP as well. I actually have it running on here if somebody just really wants to see me click on it. PaxTest and VistaProbe are both tools that will test for all of the kind of vectors that we talked about. So to look at how does this particular OS do mprotect? Can we disable things? And it has sort of a whole suite of common exploit vectors, and it will give you sort of a thumbs up, thumbs down, tell you how many bits of ASLR you have, and things like that. There's a lot of debate about it because some people will say it's very PAX-centric and the tests on OpenBSD don't apply. But it is, it's something to give you some basic level of evaluation. There's another one out there called the Attack Vector Test Platform, and there's a Johnson and Silberman talk from about 2 years ago where they went through and ran that against a lot of different exploit mitigation stuff. But PaxTest seems to be what most people are using for this. And then VistaProbe basically takes some of the PaxTest stuff and ports it to Windows. And so you can run this on your box and go, okay, here's how things look. Also, along with this talk, I'm going to have a sleepless night tonight. I had an interest in finding out, how well does this stuff really work. So I proposed to the DEF CON folks that we do stick a machine on the DEF CON LAN built with all of the exploit mitigation technologies that I could possibly shoehorn into it, and put some vulnerable services out there. And actually, kind of a corollary to that, I think either Dave LeBlanc or Mike Howard, one of the MS guys, has a blog entry where he talks about running through some of the different MS security advisories that were for 2K03 and saying whether it applies to Vista or not, which is kind of the same question. So I don't know what I'm going to build yet. I have the box built. But I'm going to probably go for a recent Apache vulnerability, some other recent exploits, and build something with FStack Protector All, aggressive ASLR, all the other things that I can possibly throw at it, and see if it's exploitable. So when I proposed that, the DEF CON guys said, yeah, it sounds really great. We want to promote it and put it out on the website. And I said, I didn't want to make it kind of about me. That was, a little too much spotlight. So I decided, what if we could get, a few hundred other people to do the same thing? So the DEF CON Own the Box contest is kind of a move back to the attackers category and defenders categories that you had in CTF a number of years ago. And CTF has kind of changed now in terms of the way it works. But I was always interested in the defenders category, and there was a lot of neat stuff that used to happen with that. And I think, without being a conspiracy theorist, I think that the fact that Immunix was a Linux project that did a whole lot of exploit mitigation stuff, the fact that the Immunix guys got second place a couple times and started to kind of move up the scoreboard made them kind of start to revisit the rules of this thing and say, okay, you can't run your own box. We're going to give you something to defend. And so the intent of this contest is to kind of bring back the defenders So we have probably about 20 boxes that are going to be stuck out on the DEF CON LAN. Not everybody is doing ASLR and NX and exploit mitigation, but they're all sort of testing their hardening stuff. And the way the contest works is if you compromise the system and get a hold of a PGP key pair that decrypts a ciphertext on the DEF CON CD, you give me the plain text and you get the box. Defenders get a t-shirt. So, but in the real world, we don't get a whole lot for the defense side either, so it's kind of the same. Kind of the same thing. The hope is that this will kind of make defense cool. Maybe that's too much of an aspiration, but at least get people kind of talking about it again. So, yeah, and thanks for sitting in, actually. And I guess if you have any questions, is it about that time?
Yeah, you've got time.
I've got time? Okay. Shoot. Anyone? Bueller? I think you were first.
So you had mentioned that the low rights Internet Explorer in Vista was less secure somehow.
Cool, thanks. Well, Vista has a mandatory integrity control, which is a kind of a MAC model. They don't like to call it MAC, but it's an integrity model. And there are different degrees, just like with SE Linux or some of the other things, there's different degrees that you can define of security levels. Vista runs at kind of IE runs at the lowest possible level. So it has kind of fewer protections than sort of other things on that platform, as I understand it.
It's my understanding that it has less rights than, so it's got increased security because it has less rights than other processes that are running
Okay.
the system. So it actually doesn't
Is it the
have
okay?
to write to files outside of a certain
Outside of the sandbox? Have you,
registry sandbox.
okay. Have you looked at the Sotorov stuff that is going on next door? I mean, I haven't really either. Okay. Yeah, and I'll tell you, I mean, honestly, and that's kind of why I had the I'm not a ninja disclaimer at the beginning of this, it's a huge topic, and there's a lot of stuff. I really struggled with how much to talk about, and so some of these things I really was kind of trying to absorb it as quickly as I could. So we'll talk more on it. But the understanding, what I will say is, the understanding that I had was that there were some things that IE does in Vista that give it a little less level of protection than other stuff. And I do know for I'm pretty sure that mProtect and Virtual Protect and things like that are in place for IE, and there are some exemptions from some of the exploit mitigation stuff. But as far as the integrity control model, that may be the case. And if I have it backwards, I'm sorry. So actually, I was going to get a picture of you guys. Should I get one first and then at the end, right? You had a question as well?
Yes, I got some customers who want to walk into your security to SE Linux, and it's kind of a nightmare thing trying to find documentation how to move services other than those that come with the distro into SE Linux and actually make it work. Do you have any recommendations on good documentation?
For the SE Linux stuff, there are some NSA docs and some other stuff for it. I think I'll be politically incorrect and say that you might want to look at AppArmor, but that may not be a popular opinion. I don't know. I mean, my personal vote on SE Linux is it does exactly what the NSA wanted, which is that it protects files and data on a system, on a multi-user system. It allows you to have a Biba model and things like that, different security levels. But for what most people running applications in private sector want, I don't know. I don't think it does it. But like I say, I'm a little biased on it, and that's why I try not to say too much specifically about SE Linux. But yeah, like I say, I think there are some NSA docs about it, about creating profiles. Red Hat has a lot of, depending on what you're running, I know Red Hat has a lot of like predefined profiles that you can use. But if it's a yeah, that's tough. And I think there's some debugging that you can do of those. You can put it in the fail open kind of mode where it's going to log those things, and then you kind of have to just build the exceptions, for it. So it's tough. Anybody else? Cool. Thank you.